Welcome to the evening session. It's a pleasure to introduce Xiaojun Chen from the University of Michigan, who will speak about some string topology-inspired structures in symplectic topology.
Okay. Okay, it's a great honor to be his student and to speak here to celebrate his 70th birthday. So in the following 20 minutes, I will introduce some results that I obtained in the understanding of some symplectic topology from string topology point of view. So our main result is the following. This is a joint with her and so the theorem is let M be an exact symplectic manifold with contact type boundary. Such that the first chain class of M is 0. Then we have the following. The first statement is there is an involutive Lie bialgebra structure on the cyclic cohomology of the Fukaya category of M of this is the Fukaya category of M. And the second statement is, well, there is a map of Lie bialgebras from the boundary. Here we assume that the manifold has a boundary. So there is a map from the Lie bialgebras from Lie bialgebra from the contact homology of the boundary of M to the cyclic cohomology of the Fukaya category. Let me just write like this: a cyclic cohomology of Fukaya category of M. Okay. The third statement is if M is the cotangent unit bundle of this means the cotangent unit bundle of N here, where N is a spin and the symplectic. Then 2 here in the second statement we have 2 homologies. Then 2 is isomorphism. And both are isomorphic to the equivariant homology of the free loop space of N. Here, we know that from Morris' talk that there is also a Lie bialgebra on the equivariant homology of N. Here, our Levi algebra is in many nature similar to his. So now I go to the details about this theorem. So, well, I cannot prove that they are the same, but you will see they're very, very similar.
Okay.
Mm-hmm.
Should be the same.
Yeah, it should be. So now, first I go to the definition of Fukaya category. I will not. Fukaya category is a kind of A infinity category, which means it is a category up to homotopy in some sense. So I will not write down the express formulas, but let me say like this. So first, the Fukaya category of M. So it is a category up to homotopy. The objects of the Fukaya category of M is well, closed is a exact closed Lagrangian manifolds submanifolds in M. In M. So here we assume that the symplectic manifold is already exact. Here the Lagrangian manifolds are also assumed to be exact, and it's also compact. We have to assume some other technical properties, which I will not discuss more precisely. It is, well, this should be a spin, and this submanifold should be a spin, and has a vanishing Maslov index. Well, the morphisms say from L1 to L2. Here, suppose L1 and L2 are two objects. Then it is defined to be the Fourier-Cochin complex of these two manifolds, which basically is the spin of, well, over, say, let's assume it's over Q, say, spin of or R. Anyway, it doesn't matter much. Spin of the intersection of two Lagrangian submanifolds. Here I put a quotation mark here. There are some technical problem when these two manifolds are not transversal. If they are not, we have to perturb one of them to by a Hamiltonian vector field. So and here the morphism is like this. So we have some A infinity operators on this. So the A infinity operators are like this: MK, which is from home of L1 to L2, LK to LK plus 1 to home of L1 to LK plus 1, which is basically counting the J-holomorphic disks with boundaries in these Lagrangian manifolds. So pictorially, it's like this: MK, like A, well, say A1. AK is equal maps to we count J-holomorphic curves like this. So the A1, A2. This is P here. The coefficient is just the number of J-holomorphic disks. Well, then now what is the cyclic homology of the Fukaya category? Well, it is well, the underlying space of cyclic Fukaya category of M. The underlying space is just the cyclic words generated by elements in this in the morphism space. So it's something like this: A1, A2, A3 till say AN. So let me put it right like this. So something like this. Now the boundary operator on this element is just take arbitrary number of these elements and put mk. So suppose we have k elements here, and apply mk on this cyclic word, and then we sum over all. So this is a boundary. Boundary is like this, and it's easy to check that this d squared is 0, and then the cyclic Cochin complex is just the dual space of M. Now,
so if you have five.
So you
have 5 terms.
Oh no, more than that. You see, you have to take cyclic. It's not necessarily start from A1. It could start from anywhere. So
How many terms are in the sum?
A lot. You sum over all possibilities.
But you have 5 groups.
Yeah.
I mean,
over K and I, say, over K and I. I is the starting, say, this is the I. Okay, now.
over I and
Yeah, right. Okay, the cyclic Cochin complex is just the dual space of this. What is the cyclic, what is the Lie algebra of this on the cyclic Cochin complex? So now, what is the definition of Lie algebra? On the vector space L is first, L is Lie algebra. And the second L is Lie coalgebra. The third is there are some compatible identities. It's something like this. If we denote the co-bracket by delta, then we have delta AB plus A delta B is equal to delta of AB. Basically, it's like this. If it is involutive, it means the following. It means you first apply co-bracket and then apply a bracket. Well, it is identically 0. Now, what is the Lie bracket? Lie bracket on the. What is the Lie bracket on the cyclic Cochin complex of Fukaya category? Third, let me write like this. More precisely, it's something like this. Suppose A, delta A is say sigma A prime tensor A double prime. Then delta A B is sigma A prime tensor. Oh no, tensor A double prime plus sigma A prime tensor A double prime B. So this is the exact meaning of that notation. Well, now what is the Lie algebra on the cyclic Cochin complex? Actually, it's given by the following. So suppose I have F and G, which lies in cyclic or M. Then the bracket of G now is also an element in this cyclic Cochin complex. Then its value, let's say A1 to AN is given by the following. Now here, this is just the cyclic word. Let me draw a picture like this. This is A1. Say this is A2, A3, till this is AN. Now, what is the bracket, the evaluation, the value of the bracket on this element? it is given by this. So you see this A1 is from L1 to L2. And this A2 is L2 to L3. So let's put, say, suppose this is AI. Well, say this is AI. And say this is AJ. Well, this is now is Li, this is Lj. Now we consider the intersection of Li with Lj. So let's assume that they intersect at P. Okay, so this is a point P. Now, it is given, this value is given by F with sum over all. So F of, well, a value on this disk, on this cyclic chain, well, let me just say something like this, right? And times G times the value on this one. So this is P. This is AI. This is am I right? So it starts from P to AI, and this is well, AJ plus 1, AJ minus 1, something like this. So we sum over all possibilities, and it's easy to check. This commutes with the boundary. So this defines a differential graded Lie algebra on the cyclic Cochin complex. Also, we can define the coproduct on the cyclic Cochin complex. Suppose I have element in the cyclic Cochin complex, then it's the value on A1 to AN tensor, say, B. What? Sum over all such possibilities. So you pick any I and any J.
And any P.
Yeah, any P. Yeah. So this is sum I, J, and P. Actually, this is a graded Lie algebra. We can check that this bracket has degree n-2, so it coincides with the one discovered in string topology. So Bm. Well, so now we have two cycles like this, and say like this is from A1 to AN, B1 to Bm. Well, here we pick Lagrange's manifold here, and pick Lagrange's manifold here. We consider their intersection. Suppose they intersect at P. Then we form a new cycle, which is something like this. We start from here, and then go through P and go to the next cycle, and then go back to the original one. So this is just the F of this new cycle.
You have to use a gluing theorem to prove there's a disk there?
No, because for example, in the transversal case, there is an intersection. So we sum over all possibility. There's no problem. And it's easier to check that it also commutes with boundary. So now, and also it satisfies condition 3, which is very similar to the one in Goldman bracket, which is also called string bracket in string topology. So now, how is this related to string topology? We have the following statement, which is about is related to the third statement here. So suppose M is T star N. Actually, we claim that the cyclic Cochin complex is quasi-isomorphic to the equivalent homology, or equivalent chain complex of N. Why is that? Actually, there is a theorem of Fukaya and Seidel and Smith, and also Nader, which says these two, Fukaya of M, restriction on n. Okay, we know that n is a Lagrangian submanifold. So now this is a derived Morita equivalent. This is a result of Fukaya, Smith, and Seidel, and also Nadler. So now the whole Fukaya category is just a quasi-isomorphic in derived sense to the Floer chain complex of n. This is just the n. And we know that, well, yeah, right. So this is Floer chain complex. So this is a derived Morita equivalent. And now we know that this is quasi-isomorphic to the singular chain complex of Cochin complex of n. This is a result of Fukaya. Well, if we use Seidel's setting, this is also proved by Abu Said. Singular. Oh, sorry. C. Singular chain complex of n. So now you see, well, we know that by homological algebra, if two categories are derived equivalent, then their cyclic homologies are the same. So the cyclic homology of Fukaya category of M, well, which is very difficult to compute, but by the result, this is just a cyclic homology of this one. And we know that this is a cyclic homology of this is the equivalent homology of the free loop space of N.
Reduced by constant loop or?
Here we don't need to reduce by constant.
You do not reduce?
No. I'm running out of time. So now we proved the statement 1 and half of statement of 3. Now let's go to statement of 2. Here we assume that M it has a boundary. So it's something like this. This is M. This is the boundary of M. We have two simplex manifolds associated to this one, which is the symplectic completion. This is a boundary of M cross R. And another one, which is just say boundary M cross R. So by a theorem of Hofer, the G homomorphic curves on these two in these two manifolds, these two simplex manifolds are like this. And also in this case, it's just like this. Here, G from in this picture, when R goes to infinity, this approach to close the Riemann orbit. And also this goes to close the Riemann orbit, and here the in infinity, negative infinity also goes to close the Riemann orbit. Now the contact homology is defined by the following. The contact is spanned. Well, the underlying space is spanned by a closed Riemann orbit, and the boundary of, say, Q, suppose Q is a G homomorphic curve, is just counting this number of, we first consider this, this is this picture, and then we have this picture. And we count G homomorphic curves like this. So this is a Q. And the boundary is, the input, the output, this is P, say, and this is P1 to Pn. And then we consider caps, which bounds this Pi. And but the first one is empty. So we sum or say P like this. Count the G homomorphic curves like this. Here, this one is a G homomorphic curve. This is also a G homomorphic curve. We count all this. And it's in simple field theory, it is proved that the boundary squared is 0. So the homology is called a contact homology. Now, how to relate this contact homology to Fukaya?
So you,
No, we count all of them. We count all of them. Here you have several outputs.
do they fit together?
Yeah, so this one is the same as this one.
Okay.
And okay, then the map from Cantal homology to let's say consider to cyclic of is given by the following. So the Q is mapped to the following. Say A1 to tensor AN. It is mapped. This is a cyclic chain. This is a cyclic chain, cyclic word generated by vector the morphisms. And this is mapped to count this. Okay, the J form, this is Q, and this is A1 to A2 to AN. So this is a number. So it assigns, it gives, well, it's easy to see this is, this count is cyclically invariant. It does not depend, it only depends on the cyclic order of these AIs. So this gives a cyclic Cochin on the Fukaya category. So this is a well-defined map. And also it's easy to check by considering the compactification of the modular, this modular space. This is a chain map. So now this gives a statement 2. Now how to prove the statement 3? Well, there is a theorem of Chilibach and Laschiff, which proved that the left-hand side is isomorphic to the equivalent homology. And also the right-hand side, by our argument over here, is isomorphic to the equivalent homology. And by a spectral sequence argument, we can show that this is, in fact, isomorphism on homology level. So I'm done.
Any questions or comments?
Could you say what the notation means, the top of the middle blackboard, that Fukaya category restricted to N?
This one?
Yeah.
Oh, here, the category, here we have several objects. We just consider one object, which is just a zero section. So it is a subcategory, actually it's an A infinity algebra.
Right.
Mm-hmm.
Any other questions?
Can you describe what that last moduli space you just drew there? What's the Riemann surface? It's got one positive puncture going to Q, and then what's
Yeah,
going
right.
on downstairs?
Yeah, so we consider this. Well, here, this is a M, and this is a symplectic completion.
Before it's mapped.
Surface? What do you mean?
the curve.
The curve, you see, this is a J-homomorphic disk with boundaries in the Lagrangian submanifolds, and the other with a singularity at the infinity. A puncture, yeah.
Can you speak it again? Now,